Welcome back to the continuation of Module 4 on the inputs needed to use the PMED software. As a reminder from Module 1 on the course schedule or roadmap, Module 4.4 overviews and discusses the layer property inputs needed to use the PMED software. Module 4.4.5 focuses on the asphalt layer material properties, which include the thermal properties, material component and volumetric properties, and the engineering response and strength properties. This will be the last submodule on layer inputs. There are 5 learning outcomes for Module 4.4.5 on the asphalt layer properties. The first is to list the key asphalt properties needed by the PMED software for pavement structural design. The second is to discuss the determination of the representative asphalt material properties for use in flexible pavement design. The third is to explain the change in the asphalt mixture properties over time or throughout the design life of the flexible pavement. The fourth is to describe the determination of the asphalt plastic strain coefficients for predicting rut depths in the asphalt layers. And the fifth is to describe the determination of the asphalt fatigue strength coefficients for predicting bottom-up fatigue cracks. Chapter 10 of the MEPDG Manual of Practice is the determination of material properties for new paving materials. Section 10.2 of Chapter 10 includes a tabulation and discussion of the asphalt layer properties and test procedures needed to determine the asphalt mixture input variables for design. This section discusses the material properties included in tables 10.2 and 10.3 of the MEPDG Manual of Practice. Now let's open section 10.2 of the MEPDG Manual of Practice. So going down to section 10.2 AC, or asphalt concrete mixtures, including SMA, asphalt treated or stabilized base layers, and asphalt permeable treated bases. So section 10.2 simply lists those properties that are needed to characterize the asphalt layers going from the wearing surface to the lower asphalt layer in a flexible pavement structure. Table 10.2 lists the asphalt materials and the test protocols for measuring the material property inputs for new and existing asphalt layers in accordance with input level 1. So the different measured properties like dynamic modulus, the plastic deformation coefficients, the sources of data, whether it's a test procedure or whether it's a default or estimated value, and then the recommended test protocol and or data source. And table 10.2 continues with the existing asphalt layer, and then the asphalt binder itself, the inputs that are required to characterize the asphalt binder, and then the different material properties, definition and discussion, And then table 10.3, the recommended input parameters and values. Those where the properties are limited or there's no testing capability for the asphalt layers. In other words, input levels 2 and or 3. The measured or property itself, and then input levels 2 and 3 in terms of how that layer property is determined. either through default values or regression equations. And then some of the default values for the different properties like Poisson's ratio, short wave surface absorptivity, thermal conductivity, heat capacity, coefficient of thermal contraction. Okay, now we'll go back to the presentation and basically continue. So this is the screenshot showing the tabs for the asphalt layer properties and input variables under the structure folder itself. The general folder or structure in the asphalt layer is where the asphalt inputs are found. There are 3 tabs for the asphalt layer properties, which are the mixture volumetrics, that's the component and volumetric mixture properties. The asphalt mechanical properties, which include the engineering response properties and the individual asphalt layers. And the asphalt AC thermal tab, which includes the thermal properties of the individual asphalt layers. The asphalt layer properties or input variables will be defined later in the module. The software will be used to show where the input parameters are located relative to the different hierarchical input levels. So now let's open the software for new asphalt layers. So under structure, we have our 3 tabs: mixture volumetrics, mechanical properties, and AC thermal for our different structures. The wearing surface and an asphalt base or multiple asphalt layers below the wearing surface. Just about all of the volumetric and mechanical properties are required for each asphalt layer in the flexible pavement. The difference is only the creep compliance, which we will illustrate and go over in a second, is only required. The creep compliance and the indirect tensile strength are only required for the wearing surface. So starting with layer 1, we have air voids are required, the effective binder content by volume, percent asphalt content by weight of mix. This is typically used in mixture design or an outcome from the mixture design process. The gradation of the aggregate blend, percent passing the 3/4 inch sieve, the 3/8 inch sieve, the number 4 and the number 200 sieves. Another property that's required for the wearing surface is what's called the gradation parameter itself, the gradation parameter. This is used for predicting top-down cracking. And so the gradation, the aggregate gradation parameter, can be calculated by the program, or it can be entered by by the designer and or user. It's generally recommended that the aggregate parameter be calculated internally by the program itself. The manual in practice does include the methodology and the equation to calculate the gradation parameter from the different sieves. The four sieves used to calculate the gradation parameter are the 3/4, the 3/8, the number 4, and the number 200% passing. Poisson's ratio, which is required for every layer in the pavement structure, can either be calculated internally by the software, or it can be entered as a constant value by the designer. In general, however the calibration was completed, either using or having the program calculate Poisson's ratio, or using a constant value for calibration, whatever is done in design should be consistent with how the transfer functions were calibrated. It's generally recommended to let the program calculate Poisson's ratio because Poisson's ratio is a function of temperature and or stiffness of the mix, and then the unit weight of the asphalt mixture itself. So all of these are required for the wearing surface. For the lower layer, again, we have air voids, effective binder content by volume, percent asphalt content by total weight of mix, the gradation. Again, the gradation parameters going to be calculated internally by the program, or the user can enter it. And then Poisson's ratio can either be calculated or a constant value can be entered. Again, it's generally recommended that Poisson's ratio be calculated, but that should be consistent, as well as the use of the gradation parameter on how the transfer functions were calculated or calibrated, and then entering the unit weight of the asphalt mixture. Okay, now starting with before we get into mechanical properties, we're going to cover the thermal properties. The thermal properties are required for each layer within the pavement, within the flexible pavement, either the wearing surface and or the base layer. All the thermal properties are required. Those thermal properties include heat capacity, thermal conductivity, aggregate, and the coefficient of thermal contraction, which can be calculated or simply the coefficient of thermal contraction can be entered by the user as a constant value. Again, this should be consistent with how the transverse cracking transfer function was calibrated, and it's generally recommended that the coefficient of thermal contraction be calibrated or calculated internally within the program. However, there are agencies that have detailed information on the asphalt mixtures where a value is entered for the mixed coefficient of thermal contraction that is binder and aggregate type specific within the agency itself. Okay, so now going to the tab on mechanical properties, and we're going to go through these starting with input level 3 first, and then we'll cover input level 2 and then input level 1. So input level 3 is where dynamic modulus is going to be calculated by the program using the Witzak dynamic modulus regression equation. The user can select, which is the common one now, the SuperPave performance grade binder type, and this can be anywhere from PG 46 minus 34 all the way to a PG 82 minus 34. Obviously, PG 64 minus 22 is the more common. We can also enter the viscosity grade, the different values or the different viscosity grades that have been used over time, or even binders that have been designated based on the penetration grade, based on the common types of penetration graded asphalt that have been specified over the years. We're going to go back and use the SuperPave binder grade for input level 3. Creep compliance, input level 3 is where the creep compliance values are calculated internally by the program for the wearing surface. And this simply, the master curve is generated by the regression equation. So the user doesn't really enter any input level 3 creep compliance values. Are all calculated. The reference temperature, which is typically 70, okay. And then the indirect tensile strength, input level 3. And again, using input level 3, the indirect tensile strength as a function of temperature is calculated internally within the program itself. So now let's go to input level 2. Input level 2 is very similar, where the dynamic modulus are being calculated by the program using the Witzak dynamic modulus regression equation. The difference is we're entering the binder data, either based on SuperPave performance grade or penetration viscosity grade. So the SuperPave performance grade can, temperature, more than one temperatures can be entered. The shear modulus from the dynamic shear rheometer and the phase angle of the binder at different temperatures are entered. The user can use one and or multiple temperatures, test temperatures of the binder for measuring the G-star or the dynamic shear rheometer in pascals, as well as the phase angle in degrees. The other thing the user can do is enter a penetration viscosity designated grades in the program. The softening point, absolute viscosity, or the softening point at 13,000 poise, the temperature. The asphalt viscosity at 140 degrees Fahrenheit, the kinematic viscosity at 275 degrees Fahrenheit, and then the specific gravity of the asphalt binder. Penetration is then entered or can be entered at one or multiple temperatures. The temperature and the penetration of the binder, as well as the Brookfield viscosity. The temperature and the Brookfield viscosity, either one or multiple temperatures of the asphalt binder. So input level 2 for creep compliance, right now there is no input level 2 in the current version, but input level 2 creep compliance will be calculated from the dynamic modulus input level 1 data entered by the user. And then input level 2 for indirect tensile strength. The user enters the indirect tensile strength at 14 degrees Fahrenheit, and then the program calculates the indirect tensile strength at other test temperatures. Okay. Now going to input level 1. Input level 1 is where dynamic modulus is measured in the laboratory at typically 5 frequencies, 0.1, 1.1 hertz, 1 hertz, 10 hertz, 25 hertz, or 0.1, 0.5 hertz is common, and then 1 hertz and 10 hertz and 25 hertz are the common frequencies, and temperatures of 14, 40, 70, 100, 130 degrees Fahrenheit. These are the common test temperatures for different frequencies, and then the value is imported in to fill this matrix of temperature versus frequency in terms of dynamic modulus value. And then the program calculates the dynamic modulus master curve. All the user has to do for input level 1 is enter the data or input the data from an XML Asphalt library, and then the program will generate the dynamic modulus master curve. For the Asphalt binder, input level 1, basically very similar to input level 2 Asphalt binder, where multiple temperatures can be used for measuring the shear modulus of the binder at different temperatures, as well as the phase angle at those temperatures. The user can also enter the penetration viscosity grade, as previously mentioned, using input level 2, which is the same. So for now, input level for creep compliance, for input level 1, basically the creep compliance is measured in the laboratory at 3 temperatures, -4 degrees Fahrenheit, 14 and 32 degrees Fahrenheit, and at loading times of 1, 2, 5, 10, 20, 50, and 100 seconds. So this is usually imported in from an XLM library where the creep compliance values have been measured for a specific type or asphalt layers specification for the wearing surface. And then the program automatically calculates the creep compliant master curve to be used in predicting transverse cracks. The reference temperature is still 70 degrees Fahrenheit, which has to do with the dynamic modulus. For indirect tensile strength with input level 1, the user measures the indirect tensile strength at different temperatures. 14 degrees is the common, and then 40 or 42 and 68 or 70, the indirect tensile strength is entered into the program. Okay, for the lower layers, basically input levels 1, 2, and 3 for dynamic modulus are all the same. There's no difference. For the wearing surface, all of these are basically the same. And the binder also is consistent with input levels for dynamic modulus. So for input level 1, then for the asphalt binder input level 1, just like it was for the wearing surface, specifying the superpave performance grade in terms of the temperatures and then the dynamic shear modulus, or from the dynamic shear rheometer, the shear modulus and the phase angle at one or multiple temperatures. And then if there's a penetration and viscosity grade, the same values are entered for as for the wearing surface. And again, one or multiple temperatures, or the penetration can be measured at one or multiple temperatures, as well as the Brookfield viscosity measured at one or multiple temperatures. Okay, so the other items under the mixture properties, there are design properties tab or folder, design property folders that include the asphalt mixture properties, which we'll cover in the presentation. One is the endurance limit, and the endurance limit, if that's applied, then the user, it typically enters an endurance limit for the specific mixture. So the endurance limit, if it was used in calibration, then it can be used in design. If the endurance limit was not used in calibration, then it should not be used in design. Typically, for the global calibration, the endurance limit was not used, and so it should not be used in design. The other item that applies is what's called the multi-layer rutting calibration. So if a user has more than one asphalt layer, the user can enter the multi-layer rutting calibration coefficients for each individual asphalt layer. If the user does not check this box, then one set of rutting calibration coefficients are used for all asphalt layers included in the structural design process. Okay, the last item in terms of the asphalt mixture properties are under calibration. And under calibration, there are an asphalt fatigue and an asphalt rutting. The asphalt fatigue, there are layer properties defined as K1, K2, and K3. We will define these later in the presentation and how they are determined for use in design, but these are derived from laboratory tests to calculate the fatigue strength of the asphalt mixture for bottom-up fatigue cracks for the lower asphalt layer. AC rutting, there are also three coefficients that are measured in the laboratory that have to do with the plastic strain or permanent deformation properties of the asphalt layer. We will also define these later in the presentation and how they are determined for a specific asphalt mixture in the laboratory, the K1, K2, and K3. So these are included under the calibration tab, and we will cover these again also in Module 6 when we talk about calibration or use of the rut depth transfer function, as well as the bottom-up fatigue cracking transfer function. We will come back to these asphalt layer properties and how they are used in the structural design process. For now, in this module on asphalt layer properties, we're going to explain how they are determined. Asphalt fatigue, bottom-up fatigue cracking, and then asphalt rutting in terms of plastic deformation. So we're going to now return to the presentation and continue with this module on asphalt layer inputs. So this slide and the next slide are simply a review with some additional information for the input variables we just discussed and illustrated in the software. This slide and the next two slides show screenshots of the Mixture Volumetrics tab, the Mixture Volumetrics tabs for the asphalt layers. The mixture volumetric properties on this screen include air voids, or will include the component and volumetric properties, and the mechanical properties are included under the engineering response properties, and the AC thermal tab includes the asphalt properties. Now moving to the mixture volumetrics tab. The mixture volumetric properties on this screen include the air voids of the mix at construction, air voids of the mix at construction, the effective binder content by volume, and the percent asphalt by weight of mix. These are important properties that have a direct input on the fatigue strength of the asphalt mixture and are used to estimate the input level 3 asphalt response properties themselves. So air voids at construction, effective binder content by volume at construction, and percent asphalt content by weight of mix at construction. Obviously, percent asphalt content by weight of mix is not going to change over time. Air voids can change over time, as well as the effective binder content by volume will change over time, simply because the air voids are changing. But these represent the values at the time of construction. This is a continuation of the Mixture Volumetrics tab. The Mixture Volumetrics on this screen include gradation in terms of percent passing the 3/4 inch sieve, the 3/8 inch sieves, the number 4 sieve, and the number 200 sieves. The gradation parameter at the bottom of the screen is defined in the MEPDG Manual of Practice. The gradation parameter is simply an index property of the gradation and is used to predict top-down cracking related to the wearing surface. It is calculated by the PMED software. However, as an option, it can also be entered by the user. It is suggested in the manual of practice, however, the designer let the software calculate the gradation parameter. This is the final screenshot of information of our inputs within the Mixture Volumetrics tab. The mixture volumetric properties on this screen include Poisson's ratio and the unit weight of the asphalt layer or mixture. Poisson's ratio is an engineering response property, but is included on this screen, as well as for many of the other materials in the pavement structure or layers in the pavement structure. Poisson's ratio can be entered by the designer as a constant value, or the designer can have the software calculate Poisson's ratio, which is dependent on temperature. The MEPDG Manual of Practice suggests that Poisson's ratio be calculated by the software, which is consistent with what was done for global calibration. The designer should use the option of user-entered or software-calculated Poisson's ratio that is consistent with the agency's calibration process. This slide and the next two slides show screenshots of the mechanical properties tab for the individual asphalt layers. The screenshot included on this slide is for dynamic modulus, input level 3. The next two slides are for dynamic modulus, input levels 2 and 1 for mechanical properties. The dynamic modulus is then followed by creep compliance and tensile strength. For dynamic modulus input level 3, the inputs needed are the volumetric properties that were shown in the previous slides or screenshots, and the binder grade designation shown in this screenshot. Although most designers are now using the SuperPave performance grade binder designation, the PMED software also includes viscosity and penetration designations of the binder. This screenshot is for dynamic modulus input level 2. The additional information or inputs required for dynamic modulus input level 2 include properties of the asphalt binder. Most designers now use the SuperPave performance grade designation, which requires the binder shear modulus and phase angle at one or more temperatures. This screenshot is for dynamic modulus input level 1. The inputs required for dynamic modulus input level 1 include the measured dynamic modulus. This screenshot shows basically blank fields in the dynamic modulus, but these would be measured values in the laboratory in accordance with AASHTO T 378 at test temperatures of 14, 40, 70, 100, and 130 degrees Fahrenheit, and at frequencies as a minimum of 0.1, 1, 10, and 25 hertz. 0.5 and or 5 hertz can also be used. For dynamic modulus input level 1, the binder properties needed are the same for dynamic modulus input level 2 shown on the previous slide. The software will then, from the laboratory measured values, the software will then calculate the dynamic modulus master curve, which we will show and discuss later in the presentation. But this, the dynamic modulus master curve does not need to be generated by the user. The software will enter or calculate or derive the master curve from the laboratory measured values of dynamic modulus as a function of temperature and loading frequency. The other mechanical properties are the indirect tensile creep compliance and strength of the asphalt wearing surface. This screenshot is for the indirect tensile creep compliance input level 2, creep compliance input level 3. The inputs required for creep compliance input level 3 include the volumetric properties and the binder designation or performance grade that was shown on the previous slides. When creep compliance input level 3 is selected, the table is automatically populated with calculated values using the regression equations embedded in the PMed software. Remember, the screenshot for the other two input levels is the same as for input level 3, with the exception that for creep compliance input level 2, the input values for each loading time and test temperature are automatically populated based on the measured dynamic modulus input values for input level 1. When the designer selects creep compliance input level 2, the measured dynamic modulus input level 1 values for the mixture must be included. For creep compliance input level 1, the measured values from AASHTO T322 are imported into the software or entered into the software. This screenshot is for the indirect tensile strength input level 3. Indirect tensile strength input level 3. The inputs required for the indirect tensile strength input level 3 include the volumetric properties and the binder designation or performance grade that were shown on the previous slides. When the indirect tensile strength input level 3 is selected, the table of strength versus temperature is automatically filled in with the input values and the indirect tensile strength at these temperatures are calculated by the regression equations embedded in the PMed software. For the indirect tensile strength input level 2, the indirect tensile strength is measured in accordance with AASHTO T322, but at only 14 degrees Fahrenheit. And the indirect tensile strengths then are automatically populated with the calculated values from the regression equation included in the software. For indirect tensile strength input level 1, the indirect tensile strengths for all temperatures are measured in accordance with AASHTO T322 for the 3 additional temperatures and entered in the software. The indirect tensile strength input level 2 is the more commonly used one by designers. So input level 2 is we're simply measuring the indirect tensile strength at only 14 degrees Fahrenheit. But for input level 1, we're measuring their indirect tensile strength at multiple test temperatures in accordance with AASHTO T322. This slide and the next slide show screenshots of the AC thermal properties for the individual asphalt layers. The thermal properties include the heat capacity, the thermal conductivity, and the coefficient of thermal contraction, which are included on this screen. As previously noted, when the software was open, the coefficient of thermal contraction, can be calculated by the software, which is the common one selected, and was used in the global calibration process, or it can be entered by the user as a calibration parameter for the length of transverse cracks. The coefficient of thermal contraction of the asphalt layer entered in the software should be consistent with the calibration process for the length of transverse cracks. So for the global calibration, the software was used to calculate the coefficient of thermal contraction. If an agency for their local calibration process used specific coefficient of thermal contraction for different aggregates and or asphalt mixtures, then those same values should be used for design to ensure that calibration and design are being used consistently. If the designer selects the option to let the software calculate the coefficient of thermal contraction of the asphalt layer, the aggregate coefficient of thermal contraction, density, and voids in the mineral aggregate are used in the regression equation to calculate the coefficient of thermal contraction. As a reminder, voids in the mineral aggregate is the effective asphalt content by volume plus the air voids. Remember, the VMA, air voids, and density are the volumetric properties after construction and not from the mixture design. The other AC thermal properties required is the asphalt surface wave absorptivity, which is included in a separate folder shown on the next slide. The AC surface shortwave thermal absorptivity is included in the software for flexible pavements under the Design Properties folder and AC Layer Properties tab. The value for the AC surface shortwave absorptivity that was used in calibration should be used as the default value for pavement design. There are other asphalt layer properties needed for design, which include the endurance limit for asphalt mixtures and the layer-dependent plastic strain or rut depth properties that are shown on this screenshot, and the AC fatigue properties and AC rut depth properties that will be shown on the next couple of slides. The endurance limit will be defined and discussed later in the module under flexural bending beam fatigue test. The endurance limit was not used in any of the global calibrations for the bottom-up fatigue cracking transfer function. So, endurance limit should not be used with the global bottom-up fatigue cracking calibration coefficients. If the endurance limit is used, it should be used during the calibration process. The rut depth plastic strain coefficients will be defined and discussed in the later in the module under rut depth or repeated load plastic strain testing. The layer dependent rut depth calibration coefficient should be consistent with the calibration process itself. If the multiple layer rutting calibration coefficients were used in calibration, then they should be used in design. If a single set of rutting calibration coefficients were used for all layers in the flexible pavement structure, then for design, those same coefficients should be used for the design process. The final input parameter included on this slide is the condition of the layer interface, which is a construction feature and not a material property. It will be discussed and defined under Module 6 on flexible and semi-rigid flexible pavement design strategies. There are two other asphalt layer material properties needed for the PMED software, and both are located in or under the calibration folder. Under the calibration folder, the AC fatigue properties tab include the fatigue strength coefficients defined as K1, K2, and K3. The fatigue strength coefficients are measured in the laboratory and are defined and explained in a latter section of this module. Also, the fatigue strength coefficients, as shown on this slide or on this screenshot, are only applicable to bottom-up fatigue cracking, which is determined from the lower dense graded asphalt layer itself. That also will be explained in more detail under Module 6 for the bottom-up fatigue cracking transfer function. The AC rutting properties tab include the asphalt rut depth or plastic strain coefficients that are defined as K1, K2, K3. These coefficients are also under the calibration folder, but under the AC rutting tab. The asphalt rut depth coefficients are measured in the laboratory and are defined and explained in a latter section of this module. And it will also be further explained in Module 6 on the flexible pavement design. Before getting into the individual asphalt layer properties that were illustrated in the software and in the screenshots, an understanding of how the properties are determined and what they represent is provided on this slide. As for the other processed materials, the structural design is completed prior to the contract being let. In other words, the contract is unknown, or the contractor is unknown, and the asphalt mixture has yet to be produced for the project. So the question becomes, as well as for other processed materials, where do the asphalt material component and mixture properties come from? Just like for the other processed materials, this is where the agency's material and construction specifications and the historical construction database become important and is the tie between structural design and construction. For the different asphalt mixtures specified by the agency and placed by the contractor, the average values for the asphalt material input variables that meet the construction specifications and were found to be acceptable should be determined from the historical or previous year's construction data. Many agencies have created asphalt XML material library files for the asphalt mixtures included in the agency's asphalt construction specifications. This allows the designer to select an asphalt mixture when completing the flexible pavement structural design process with confidence, and also reduces the probability of blunders from the user making an error or typo in entering the data or the input value into the software. So using the or creating and using the XML input library files is strongly encouraged for use in design. This section now focuses on the asphalt binder properties for the asphalt layers. The asphalt binder property test procedures are listed on this slide. Remember, the multiple stress creep recovery asphalt designation is not in the current version of the software. The multiple stress creep recovery designation or specification is planned to be included in the PMED's version that will be released for fiscal year 2024 or in July 2024. So the multiple stress creep recovery asphalt designation should be applicable for use in the version released in July 2024. But the table also lists the other asphalt binder properties that are now required or used by the software for predicting pavement distress in terms of calculating some of the binder response, not the binder, but the mixture response and strength properties of the mix. The asphalt binder is characterized by three different types of binder designation, as we noted when we illustrated the software. The first is the performance grade or PG designation, which is now the common one used. This is the common binder specification used just about all of the state agencies in North America. The second and the performance grade specification requires a Brookfield viscosity measured in accordance with AASHTO T316, and then a complex shear modulus and phase angle measured in accordance with AASHTO T135. The second and third are the penetration and viscosity based specifications. The penetration is measured in accordance with AASHTO T349 or T49. The ring and ball temperature required is measured in accordance with AASHTO T53. The absolute viscosity measured in accordance with AASHTO T202, and the kinematic viscosity measured in accordance with AASHTO T201. The asphalt-specific gravity is also required for all, and is measured in accordance with AASHTO T228. The designer can select either of the three designations, either the performance grade designation, the penetration designation, or the viscosity-based designation. For input level 3, just the binder designation is needed. The binder property used by the program represents overall averages within each binder designation. For input level 2, The properties are measured in accordance with the test method listed on the slide. For input level 1, the same binder properties are required for input level 2. Examples of the complex shear modulus and phase angle are displayed on this slide for a PG 58-28 binder. For input level 3, only the PG 58-28 is required for the binder. For inputs level 1 and 2, the shear modulus, the complex shear modulus, and the phase angle for the binder are needed for one or more temperatures. And again, this example is for a PG 58-28. So whatever binder designation is selected or binder type is selected within the specification, then for inputs level 1 and 2, the complex shear modulus and the phase angle are entered at one or multiple test temperatures for that binder. This section is now going to focus on the thermal, volumetric, and component properties of the asphalt layer. The asphalt mixture thermal property test procedures are listed on this slide. Remember, the values entered for the thermal properties should be consistent with the value used for the calibration process. The majority of agencies simply use the default values for the thermal properties, which were also used in the global calibration process. Again, as a reminder, the user or designer should select the default values that are or were consistent with the calibration process. And again, remember, the software can either calculate the coefficient of thermal contraction or a single value can be entered by the user. And again, whether it's calculated from the software or a value entered by the user, that should be consistent with how the calibration was performed. For the global calibration, the software was used to calculate the coefficient of thermal expansion and/or contraction. The asphalt mixture component volumetric property test procedure are listed in this table. Remember, the volumetric property values entered in the PMED software should represent the values at the time of construction. They are not the mixture design values. This section focuses on the strength and structural response properties for the asphalt layer. The asphalt mixture response and strength property test procedures are listed on this slide. Remember, Poisson's ratio can be estimated using the default value entered by the user or calculated by the software. The options selected should be consistent with the calibration process. The dynamic modulus values are measured in accordance with AASHTO T378. The indirect tensile creep compliance and strength values are measured in accordance with AASHTO T322. Both the creep compliance and strength in accordance with AASHTO T322. The repeated load Plastic deformation or strain values are measured in accordance with the method of test included in NCHRP Report 719 for determining the asphalt layer repeated load strain. A draft standard method of test consistent with the method described in NCHRP Report 719 was prepared and is available for use, but has yet to be balloted through AASHTO. The fatigue strength values are measured in accordance with AASHTO T321. As noted for the other asphalt layer properties, the asphalt layer strength and structural response properties should be measured on specimens representative of the condition after construction and not at the design laboratory volumetric properties. The condition after construction represents short-term aged asphalt mixtures. We will now go through the strength and structural response properties and discuss the reasons for using short-term aged rather than long-term aged specimens. Poisson's ratio is the same as defined for the other pavement materials discussed in the earlier modules of this course. Poisson's ratio is used with a dynamic modulus to calculate the critical responses in the asphalt layer over time. As such, it should represent short-term aged specimens. This section focuses on dynamic modulus of asphalt mixtures or layers. The dynamic modulus is measured in accordance with AASHTO T378, which is a stress-controlled uniaxial, which is unconfined, or confined test. The dynamic modulus is measured over a range of loading frequencies and temperatures so that a dynamic modulus curve can be generated by the PMID software. The cyclic deviator or uniaxial stress is applied using a sinusoidal waveform where both the applied stress and resultant vertical deformations are measured. The peak applied stress and the peak vertical deformations are used to calculate dynamic modulus. The phase angle of the mixture is also measured during testing. This slide includes a short video clip of the dynamic modulus test. There's not much to see in terms of the response of the test specimen because the load and measured deformations are small to ensure the load does not damage the test specimen. The dynamic modulus option being used for testing this specimen is the unconfined condition or uniaxial type test. In other words, no membrane is used to encase the specimen. The confined test is the same as for the confined test is the same as for the unconfined test, except that a membrane encapsulates the specimen. The dynamic modulus measured on an unconfined test specimen, as illustrated in this video, will be consistently less than the dynamic modulus measured on a confined or triaxial type specimen. As such, the condition of unconfined and confined should not be mixed to ensure input compatibility. AASHTO T378 is the dynamic modulus test procedure and is a stress-controlled type test, and the cyclic deviator or uniaxial stress is applied using a sinusoidal waveform where both the applied stress and resultant vertical deflection are measured. The peak applied stress and the peak vertical deformation, peak applied stress and peak applied vertical deformation are used to calculate dynamic modulus. The phase angle of the mixture is also used or measured during testing. The phase angle is described as the time lag between the applied stress in the black solid curve and the measured deformation as illustrated in the dashed red curve and is illustrated in this simulation of the applied load and deformation response of the specimen. The phase angle provides information regarding the elasticity of the mixture and is illustrated in the next slide. This is an expanded simulation of one of the loading cycles from the previous slide. One of the loading cycles from this slide, both the load being applied and the resultant deformation being measured, deformation or strain. And shows a graphical definition of the phase angle. So the phase angle is defined as the time lag or difference between the maximum applied stress, the stress applied, maximum applied stress, and the maximum measured deformation and or strain. Measured deformation and or strain. So it's the time lag or difference between the peak stress and peak measured strain of the specimen. A low phase angle, in other words, where the time lag is small, means the material behaves more like a linear elastic material. A perfectly elastic material has a phase angle of 0 and means there is no lag between the applied stress and the measured response of the specimen. In other words, the maximum measured stress occurs at the same time as the maximum measured strain and or deformation. A high phase angle or very large difference between the maximum applied stress and when the maximum applied strain or deformation occurs means the material is beginning to behave as a viscous material. A purely viscous material has a phase angle of 90 degrees, and there is a long time between the maximum applied load and when the maximum measured response occurs. This table shows the dynamic modulus and test parameters for each input level as a summary. Input level 3 only requires the volumetric properties and grade designations of the asphalt binder. Dynamic modulus is then calculated using the dynamic modulus Witzak regression equation embedded in the Pavement ME software. Input level 2 requires the volumetric properties and also requires the measured properties of the asphalt binder. The measured properties of the asphalt binder depends on whether the binder specification is based on the performance grade system, a viscosity-based system or designation, or the penetration-based system or designation. And then using the volumetric properties and component properties and the binder properties, the dynamic shear modulus are calculated using the Witzak regression equation, and then those properties are varied over time for aging. Input level 1 requires the measured dynamic modulus in accordance with AASHTO T378 at different mixed temperatures and mixed loading frequencies, and as well as the asphalt binder mixture properties that were also required for input level 2. The asphalt binder properties are used in calculating the dynamic modulus at different frequencies and temperatures, and in aging the asphalt binder and mixture over time. They are not directly used to create the dynamic modulus master curve internally within the PMET software. And again, the dynamic modulus master curve is generated by the software itself. The user does not need to generate or create the dynamic modulus master curve. This chart illustrates the stiffness of an asphalt mixture as a function of temperature. Dynamic modulus as a function of temperature, and illustrates the temperature susceptibility of different mixtures, as well as loading frequency. So dynamic modulus as a function of temperature, test temperature for different loading frequencies. Very low loading frequencies versus very high loading frequency, 25 hertz versus 0.1 hertz. At low temperatures, asphalt binders are much stiffer than at higher temperatures. And as the temperature increases, the dynamic modulus decreases. At very short loading times or high loading frequencies, the stiffness of the binder and thus the stiffness of the mixture will approach the elastic or shear modulus in terms of a linear relationship between stress and strain. So very high loading frequencies increases the stiffness of the mixture, and usually it is less temperature susceptible. The PMET software uses the viscoelastic characteristics of the asphalt mixture to estimate the stiffness of the asphalt layer with different truck speeds and daily as well as seasonal variations in temperature with depth. This chart simply illustrates the dynamic modulus as a function of loading frequency. Dynamic modulus as a function of loading frequency for different temperatures. High temperatures to much lower test temperatures. As shown, as the test frequency increases or the loading time decreases, dynamic modulus increases. The impact of frequency is less at the colder temperatures or lower temperatures because the asphalt behaves more like an elastic material at the lower temperatures in comparison to the higher test temperatures. Test specimen preparation is critical for testing just about any material, including asphalt mixtures. This slide simply shows test specimen preparation activities in accordance with AASHTO T378 for the dynamic modulus tests, going from sample compaction to sawing the test specimen from the gyratory compacted sample, to sawing the ends of the specimen for creating the test specimen. Dynamic modulus test specimens are produced by compacting taller gyratory specimens at least 170 millimeters tall and 150 millimeters in diameter, and then coring out the inner 100 millimeter diameter core. The ends of the core are then sawed and or trimmed to the final length of 150 millimeters. There are other small scale specimens not shown on the slide that are also applicable for dynamic modulus test. The reason for sawing the test specimens from the interior of a gyratory compacted sample is to achieve uniform air void distribution and or uniform density throughout the sample. Previous studies have shown that the gyratory compactor produces specimens with unequal air void distributions throughout the specimens. Air void levels increase toward the outside of the gyratory cylinder, so getting the test specimen from the interior reduces the variation in air voids throughout the specimen. Again, the air voids used for measuring dynamic modulus and the other strength and response properties of the asphalt mixture should represent the time at construction. This slide illustrates attaching the displacement measuring devices, which are the linear variable differential transformer, or LVDTs, on the test specimen for measuring deformation, for calculating dynamic modulus and phase angle. The dynamic modulus test is usually performed without confinement, but confinement or confined triaxial test specimens can be applied. For confinement, a membrane is placed over the test specimen and the LVDTs are attached to the specimen through the membrane and then sealed, as shown in the illustration in the center slide. The illustration or photo to the right is an unconfined uniaxial test specimen. There are devices available to assist in attaching the LVDTs to the specimen to ensure the uniaxial deformation devices are attached at the correct location and properly aligned on the specimen to reduce variability of the measured displacements. Reducing test variability means we can test fewer specimens at the same confidence level or for the same confidence level. This is an example of dynamic modulus test results. The same gradation in percent asphalt was used, but with 3 different asphalt binder grades: a PG 76 minus 22, PG 70 minus 22, and a PG 64 minus 22. Dynamic modulus test results show that little to no difference in modulus or stiffness is observed at the low test temperatures for the 3 different types of binders. This is expected as all 3 asphalt binders have a low temperature PG of a minus 22 degrees centigrade. However, at the intermediate and especially at the high test temperature, there is a clear difference between the 3 binders. The PG 76 minus 22 is a stiffer binder. 76 minus 22 is a stiffer binder and has a higher dynamic modulus value, while the PG 64 is a softer binder and has the lower dynamic modulus values at the higher test temperatures. The PMED software uses the concept of the time-temperature superposition principle to create or generate a master curve for the asphalt layers. This chart illustrates a typical dynamic modulus master curve that is generated by the software from the dynamic modulus test results measured in accordance with AASHTO T 378. The concept of time temperature superposition is used to determine the asphalt layer stiffness for different truck speeds with layer depth and throughout the year and design period itself. The coefficients of the master curve are not entered into the PMED software. Only a tabular listing of the measured dynamic modulus are entered in the software at different temperatures and loading frequencies as graphically illustrated on this slide. So the individual dynamic modulus measured at different temperatures and loading frequencies are used to generate the master curve. The master curve is created in accordance with AASHTO R62, the standard practice for developing dynamic modulus master curve for asphalt mixtures. Most data acquisition systems that come with the asphalt mixture performance tester have a built-in procedure for shifting the dynamic modulus data to create the master curve. These data acquisition systems report the actual dynamic modulus values as well as the coefficients of the master curve as outcomes from the test. For the PMED software, however, only the tabular listing of dynamic values are entered in the software. This slide includes a graphical illustration for shifting the measured dynamic modulus data in accordance with time temperature superposition to create the mixture specific master curve. Basically, there is a reference temperature, typically 70 degrees Fahrenheit, and the measured dynamic modulus values are shifted to form a master curve between the reduced time, and modulus. The lower test temperatures are those below the reference temperatures. The dynamic modulus are shifted to the left, or a reduced loading time or higher frequency. Higher test temperatures are those above the reference temperature. The dynamic modulus values are shifted to the right, or a longer loading time or lower frequency. The shifting is done mathematically through a shifting function to minimize the differences between the measured dynamic modulus and shifted calculated dynamic modulus to develop the master curve. And the shift function is shown on the slide. There are different forms of the shift functions that can be used. One is defined as the 5-parameter shift function, and the other as the 7-parameter shift function. The one illustrated or shown in this chart is the 5-parameter shift model or shift function. The one selected should be consistent with the shift function used during the calibration process itself. This chart is a graphical illustration of the master curve that was created from the dynamic modulus values shown on the previous slide, along with a sigmoidal shift function used to determine the shift factors. The following defines the parameters of the sigmoidal shift function. E star is the dynamic modulus that's measured in the laboratory. TR, or T subscript R, is the reduced testing time, and the coefficients of gamma, beta, alpha, and delta are regression coefficients determined from fitting the data to create a master curve. Use or application of the time-temperature superposition principle has been checked and confirmed through many different studies and is applicable to asphalt mixtures across the typical temperature range used to test asphalt mixtures. The master curve is created internally within the PMED software and used to determine the dynamic modulus values as a function of pavement depth, traffic speed, and mix or layer temperature. Most designers and laboratory technicians typically use the actual dynamic modulus values themselves in comparing the stiffnesses between different asphalt mixtures, rather than comparing the coefficients from the master curve. The coefficients generated from the master curve exhibit less difference between significantly different mixes than the actual dynamic modulus values, because the coefficients are determined or derived over a wide range of temperatures and loading frequencies. This table shows two examples of dynamic modulus values measured at different test temperatures and loading frequencies defined in AASHTO T378. As displayed, the mixture simulated in the upper table is a stiffer mix compared to the second or lower table. The dynamic modulus measured at 130 degrees Fahrenheit and 0.1 loading frequency is almost 27,000, while the dynamic modulus for the other mixture at the same temperature and loading frequency is just over 7,000 psi. The PMAT software takes the dynamic modulus values that are entered in the software and creates and creates the dynamic modulus master curve. The designer does not need to calculate the master curve unless they just want to in evaluating the test or measured values. As a reminder of 2 points, the asphalt binder properties are used in aging the asphalt mixture over time. They are not directly used to create dynamic modulus master curve internally within the PMET software. And the second point, there is a consistent difference in the measured dynamic modulus between the confined or triaxial and unconfined or uniaxial test condition. So input compatibility and being consistent with how the transfer functions were calibrated, either using unconfined or confined tests, is important. These two graphs are simply the simulation of the master curve or the master curve created for these two sets of data. This chart shows a graphical illustration of the calculated dynamic modulus values over 4 years, construction year 1, year 2, year 3, year 4, for a specific mixture and different layer thicknesses. The asphalt layers are divided into sublayers, and the dynamic modulus for the upper or surface layer is higher than for the lower asphalt layer because the frequency or the time of loading is lower at the surface compared to the lower layers. So these are the sublayers that the program divides the asphalt layers into. And then the dynamic modulus is dependent upon the time of loading between the surface, the mixture that feels the load at the surface, and the lower asphalt layer that feels the load, truck load, over a longer period of time or lower frequency. So the modulus of the wearing surface will always be higher than the modulus of the lower asphalt layer on relatively thick asphalt pavements. And that's due to truck speed and or temperature differences from the top to the bottom of the asphalt layers. Remember, the PMAT software assumes the daily truck traffic for flexible pavements is equally distributed between the hours of a day. As a reminder, the truck traffic hourly distribution factors are not used for flexible pavements. The hourly distribution factors are only applicable to rigid pavement design. This assumption and difference will be discussed again and included in Module 5 for rigid pavement design and Module 6 for flexible and semi-rigid pavement design. So the program calculates modulus as a function of season, as well as a function of season or age, as well as a function of depth within the asphalt structure. So given that, now that we have discussed dynamic modulus of the asphalt layer, let's ask a general question about the impact of dynamic modulus on performance. This chart shows the dynamic modulus master curves for 5 dense graded asphalt mixtures. Which of these dense graded asphalt mixtures would have the lower predicted or calculated distress for rut depth, transverse cracks, and or bottom-up fatigue cracks. So just a little time for the reviewer to think about which of these mixes would exhibit the lower rut depths, the lower transverse lengths of transverse cracks, and or the lower amounts of bottom-up fatigue cracks. For rut depths, mix D, or the black triangles, would have the lowest predicted rut depths because it has the higher dynamic modulus values. For transverse cracks, mix C, or the green crossed curve, or plus sign, the green plus sign curve. Mix C would have the lowest length of predicted transverse cracks because it has the lower dynamic modulus values. For bottom-up fatigue cracks, mix D would have the smallest area of predicted bottom-up fatigue cracks. In other words, it's the stiffest mixture. We will use this graph and come back to this example in Module 6 when we start explaining and discussing the distress transfer functions for flexible pavements in terms of explaining the reason why mix D would exhibit the better performance in terms of bottom-up fatigue cracks, lower amounts of bottom-up fatigue cracks, and lower lengths of transverse cracks, while mix C would exhibit the better performance in terms of lower mix D and C, mix D would exhibit the better performance for the bottom-up fatigue cracks and the lower amounts of rutting because it's a stiffer mix, while mix C would exhibit the better performance in terms of lower amounts of transverse cracks because it is more compliant or has a lower dynamic modulus. This section now focuses on the indirect tensile creep compliance and strength of asphalt mixtures and or wearing surface layers. The indirect tensile creep compliance and creep and strength are measured to evaluate and predict an asphalt wearing surface's resistance to low temperature cracking or predict the length of transverse cracks. Both the creep compliance and strength are measured in accordance with AASHTO T322. The creep compliance and strength are used in a thermal viscoelastic analysis model to calculate tensile stress at the surface of the wearing surface and then compare the indirect tensile strength to the tensile stress for predicting transverse cracks over time. This section simply discusses the input variables and values, while Section 6 on flexible pavement design will discuss use of the inputs to predict the length of transverse cracks. This slide includes a short video clip of the indirect tensile creep compliance test. Again, there's not much to see in terms of the response of the test specimen because the lower loads are used so that the specimen does not fail in creep or does not fracture. The video The video clip did not show, or did show, the LVDTs attached to each surface of the specimen. In other words, there's LVDTs that are attached to this side of the specimen, and there's also a set of LVDTs to measure vertical and horizontal displacement on the opposite side of this test specimen. Creep compliance of the asphalt wearing surface is determined in accordance with AASHTO T 322. In summary, a constant load, is applied rapidly and held constant along the diametral axis of the indirect tensile specimen. LVDTs are used to measure both the horizontal as well as vertical displacement along the center of both sides of the specimen for a total loading time of 100 seconds, at which the load is rapidly removed. 3 test temperatures are used for measuring creep compliance: -4, 14, and 32 degrees Fahrenheit. The tensile stress and horizontal and vertical strains are measured and are used to determine the creep compliance, defined as the integral J subscript T on this slide, and Poisson's ratio. Creep compliance is calculated as the inverse of modulus, or the tensile or horizontal strain divided by the tensile stress from the applied load, the applied tensile stress. Poisson's ratio can be calculated for the colder temperatures and is the same as previously defined in the section. However, a Poisson's ratio measured at low temperatures is not necessarily representative of the Poisson's ratio measured at much higher test temperatures for fatigue cracking and plastic deformation or rutting, because Poisson's ratio is temperature and or asphalt layer stiffness dependent. Remember from an earlier section of this modulus, Poisson's ratio, consistent with its use in calibration, should be used in design. This table is simply a summary and shows the creep compliance and strength and test parameters for each input level. Input level 3 only requires the volumetric properties and binder grade designation. The creep compliance and strength values are calculated from the regression equation included in the PMED software. So only the binder grade and volumetric properties are needed. For input level 2, the creep compliance measured or calculated or derived from the measured or input level 1 dynamic modulus values, or AASHTO T 378. The strength is measured in the laboratory at 14 degrees Fahrenheit in accordance with AASHTO T 322. For input level 1, the creep compliance values are measured in the laboratory in accordance with AASHTO 322 at test temperatures of a -4, 14, and 32 degrees Fahrenheit. The strength is measured in the laboratory at 14 degrees Fahrenheit, as well as other test temperatures in accordance with AASHTO 322. The creep compliance and strength values are not increased or changed over time. In other words, aging is not applied to the indirect tensile creep compliance and strength values. The measured values represent short-term age test specimens after construction. The aging condition will be discussed in more depth in Module 6 on flexible pavement design. The indirect tensile test apparatus is shown in this slide. The super-paved gyratory compactor is used to compact a sample, and the test specimen is sawed to the defined thickness as also shown at 50 millimeters. The equipment typically consists of a servo hydraulic loading frame, environmental chamber, and computer-controlled data acquisition system. The photograph on the left shows the outside of the environmental chamber and monitor used to conduct the indirect tensile creep compliance and tensile strength test. The center photograph shows the specimen inside the environmental chamber ready for testing, along with the LVDTs attached to both faces of the specimen. The photograph on the right simply shows a close-up of the on-sample instrumentation required to measure the horizontal as well as vertical displacements used to calculate the creep compliance values. These two charts simply illustrate the creep compliance as a function of loading time for three different test temperatures, -4, 14, and 32 degrees Fahrenheit, or -0 degrees C, 10 degrees C, and 20 degrees C. The upper chart illustrates the creep compliance for a dense graded asphalt mix with a high amount of recycled asphalt pavement material or wrap, and the lower chart illustrates the creep compliance for a dense graded polymer modified asphalt mixture. As shown, creep compliance increases with longer loading times. Again, creep compliance as a function of loading time. So creep compliance increases with an increase in loading time and or higher test temperatures. The gray dashed line is 0 degrees C. The blue solid line, closed circle solid line, is -10 degrees C, and the red dashed line is a -20 degrees C. So creep compliance increases with longer loading times and higher test temperatures. For dense graded asphalt mixtures, the measured creep compliance values do not significantly increase for the colder test temperature of a -4 degrees Fahrenheit or -20 degrees centigrade. While there is a substantial increase in creep compliance for the longer loading time, measured at 32 degrees centigrade or 32 degrees Fahrenheit or 0 degrees centigrade. At the colder test temperatures, the dense graded mixture is behaving more like an elastic material, and as the test temperature increases, the viscoelastic component becomes more predominant. For both types of mixes, the high wrap mix as well as the polymer modified mix. The PMED software uses the concept of or principle of time temperature superposition to develop a creep compliance master curve for the wearing surface mixture. In concept, use of the time temperature superposition principle discussed for dynamic modulus is the same as for creating the creep compliance master curve. The reference temperature for creep compliance, however, is minus 20 degrees centigrade, while 70 degrees Fahrenheit was used for the dynamic modulus. So the creep compliance data measured at the higher test temperatures gets shifted to the left of the colder temperature through the shift factor function, just like for the dynamic modulus values. Use or application of the time temperature superposition principle has been checked and confirmed through many different studies and is applicable to asphalt mixtures across the typical temperature range used to test asphalt mixtures. So the master curve is created by shifting the data to the reference, the actual lab creep compliance data to the reference temperature in accordance with the shift function and or factors, similar to the dynamic modulus master curve. This chart includes a graphical illustration of the creep compliance master curve. Like the dynamic modulus master curve, a sigmoidal shift function is used to determine the shift factors, and the coefficients from that shifting process are used within the PMED software. As the creep compliance increases, the ability to build up tensile stresses in the mixture as the temperature decreases. In other words, there's less buildup of tensile stresses the more compliant or the higher the compliant of the mixture. So the tensile stresses from a drop in temperature is lower with higher creep compliance values. Stated conversely, as the relaxation modulus or the tensile stress divided by the tensile strain decreases, the tensile stress will decrease as the mixture relaxes, and the lower the probability for cracks to develop. Like for dynamic modulus, most users typically use the actual creep compliance values themselves in comparing different asphalt wearing surface mixtures rather than comparing the coefficients of the creep compliance master curve for the same reason given previously for dynamic modulus. This table shown on this slide is an example of the creep compliance values measured at the different test temperatures and loading times as defined in AASHTO T322. The PMED software takes the creep compliance values that are entered in the software and creates the creep compliance master curve. The designer does not need to calculate the master curve unless they want to in evaluating the test or measured values themselves. This table shown on this slide is another example of the creep compliance values measured at different test temperatures and loading frequency as freak times as defined in AASHTO T322. The creep compliance master curve created by the PMED software is illustrated in the chart also shown on the slide. The charts from the previous two slides are shown on this slide together to compare the creep compliance values between the two dense graded wearing surface mixtures. The chart on the left is for the asphalt mixture with a high percentage of wrap, while the chart on the right is one for the different asphalt and with a lower temperature grade and no wrap. The creep compliance values displayed in the chart on the left are much lower than for the chart with the different asphalt grade and no wrap on the right. The creep compliance values for the wrap mixture for the colder temperature and short loading time is slightly lower than the mixture without wrap without wrap, 3.0 times 10 to the minus 7 compared to 3.8 times 10 to the minus 8 times 10 to the minus 7. At the higher test temperature and longer loading times, the creep compliance value is substantially lower for the mixture with the wrap, shown on the left chart, than for the mixture without wrap, shown on the right chart. A creep compliance value of 2.8 times 10 to the minus 6 for the mixture with wrap, compared to a creep compliance value of 1.44 times e to the minus 5. So the polymer modified mixture without wrap is much more compliant than the dense graded mixture with higher amounts of wrap. So the mixture designated by the chart on the right will exhibit lower amounts of transverse cracks. Now that we've discussed the creep compliance of the asphalt wearing surface mixtures, let's ask a question about their impact on performance or the length of transverse crack. This chart shows the creep compliance master curves for 8 dense graded surface mixtures. Which of these asphalt mixtures would have the shortest predicted length of transverse cracks? And again, we will give a little time for the user or the reviewer to view the mixes and then pick a mix on what is more resistance to transverse crack or should exhibit lower amounts of transverse cracking. Wearing surface mixtures defined as the Warren mix, and that's the cross solid line, would have the shortest length of transverse crack predicted by the PMET software. The wearing surface mixtures having the greatest length of transverse cracks predicted by the PMET software would be the mixture defined as the Blair mix, and that's the less compliant, has the lower creep compliance values, the Blair mix, while the Warren mix has the highest creep compliance values and is more compliant. So it's more resistant to transverse cracks. The indirect tensile strength of the asphalt wearing surface is determined in accordance with AASHTO T322 and is only measured at 14 degrees Fahrenheit or minus 10 degrees centigrade for inputs level 1 and 2. As summarized in a previous slide, the indirect tensile strength is calculated from the asphalt grade, designation, and volumetric properties for input level 3. The indirect tensile strength is used to compare the tensile stresses computed at the surface when the temperature decreases to determine if a crack is going to initiate. In summary, the load is applied at a constant deformation rate of 50 millimeters per minute or 12 inches per minute until failure or the test specimen fails or a crack occurs. The strength of the mixture is simply the maximum stress observed and or maximum load measured. The relationship used to calculate tensile strength is included in the MEPDG Manual of Practice. The test may be conducted over a range of temperatures and aging conditions. Strain is sometimes monitored during the test depending on how the data will be used. The tensile stress and horizontal and vertical strains are measured and are used to determine creep compliance, defined as J subscript T and Poisson's ratio, which is explained and mathematically illustrated in the MEPDG Manual of Practice. Creep compliance is calculated as the inverse of modulus, or the time or horizontal strain, divided by tensile stress from the applied load. Poisson's ratio can be calculated for the colder temperatures and is the same as previously defined in this section. This slide includes a short video clip of the indirect tensile strength test. The video illustrates the crack occurring at a higher test temperature to see the crack occurring along the diametral axis. At the higher test temperature, the crack will typically propagate around the aggregate particles, but at low test temperatures, the crack will typically go through the larger aggregate particles. So it was observed that a crack occurred and goes around the larger aggregate particles because it's at a higher test temperature. Indirect tensile strengths measured at the colder test temperature, the cracks sometimes go through the larger aggregate particles. Again, depending on the aggregate type and adhesion between the asphalt and aggregate. The indirect tensile strength of the asphalt wearing surface is determined in accordance with AASHTO T322, as mentioned on the previous slide. This slide also shows typical details of the test specimen geometry, in other words, the height as well as the diameter of the test specimen. A 50 millimeter per minute loading rate is used in applying the load along the diametral axis. The diametral axis. In some cases, the horizontal as well as vertical deformations are measured during the indirect tensile strength test. And then the tensile strength at peak load is calculated by the equation shown on the slide, as well as in the MEPDG Manual of Practice, and as well as designated in AASHTO T322. This section focuses on measuring the plastic deformation and deriving the plastic strain coefficients of the asphalt layers, including the wearing surface to the asphalt base layers. The incremental and cumulative measured plastic strains and coefficients derived from a repeated load plastic deformation test in accordance with the method of test documented in NCHRP Report 719 are used to predict rut depth in the asphalt layers. This section discusses the input variables and values, while Section 6 on flexible pavement design will discuss use of the inputs to predict the rut depth in the asphalt layers. This slide includes a short video clip of the repeated load plastic deformation test in accordance with the test method described in NCHRP report number 719, and the AASHTO standard method of test was prepared for AASHTO, but it has yet to be balloted in 2023. The method of test is available through AASHTOware. There is not much to see in this video in terms of the specimen response, because the deformations are usually low for a well-graded and rut depth resistant mixture. The video does capture the monitor showing the deformations measured by the LVDTs and the repeated load applied to the specimen. This is also a confined test or a triaxial test where a confining pressure is applied to the specimen. So the load and deformations were shown on the monitor in the video. This slide summarizes the testing conditions of the repeated load plastic deformation test. This test is conducted at one or multiple test temperatures using 10 psi confinement, and the specimen is encased in a membrane with a deviator stress of 70 psi. The tests were run to the lesser of 10,000 loading cycles, or a cumulative permanent axial strain of 5%. The test can exhibit high variability, so triplicate specimens and 3 test specimens are recommended for use. The test procedure presented in NCHRP Report 719 and the AASHTO standard method of test allows one test temperature to be used, and that temperature is the equivalent rut depth temperature. NCHR Report 719 and the AASHTO method of test include information for determining the equivalent rut depth temperature. One temperature is generally considered sufficient when used on a mixture design basis, while the 3 test temperatures are suggested for determining the rut depth coefficients of the MEPDG rut depth transfer function. And the rut depth transfer function are explained in Module 6. The 3 test temperatures suggested are 20 degrees centigrade, the 7-day average maximum temperature from LTPP bind -5 degrees centigrade, and an intermediate temperature midway between the lower and upper temperatures. The cumulative plastic deformation or axial strain outcome from the repeated load plastic deformation test is illustrated in this chart by the solid black line, which is the log of the number of load cycles versus the log of cumulative plastic axial strain measured from the repeated load plastic deformation test. The cumulative strain versus number of load applications or cycles relationship is grouped into three categories or three regions: the primary region, the secondary region or steady state region, and the tertiary region. The primary region is where the plastic axial strain increases but at a decreasing rate with number of load cycles. The steady state region is where the rate of change in the plastic axial strain is constant with the number of load cycles, or there is a linear line between the log of the number of load cycles versus the log of the cumulative axial plastic strain, the steady state region. The tertiary region is where the plastic axial strain increases at an increasing rate with number of load cycles. Well-designed asphalt mixtures or mixtures resistant to rutting do not usually exhibit the tertiary region or accelerated flow of the mix. There are two typical patterns which are not shown on this slide, or two other patterns not shown on this slide. One pattern does not include the tertiary region, and that pattern is described in NCHRP report number 719. The other pattern also does not include the tertiary zone, but includes where the axial plastic strain increases but at a decreasing rate. So the two other categories of plastic deformation are not included on this slide, but are included in the NCHRP report number 719. The interpretation of the cumulative plastic strain measured at one test temperature includes determining the two parameters from the test: the slope, S sub t, and the intercept, I sub t, from the steady state range. These two parameters are referred to as the plastic deformation characteristics or parameters of asphalt concrete mixtures and are used to predict rutting over time. With only one test temperature, the temperature term T and its exponent B sub T are not directly determined. but from multiple test temperatures, the temperature exponent can be derived. So the two important for a single test or a single temperature, the two important parameters from the plastic strain or deformation test is the S sub t, which is the exponent of the number of loading cycles or the slope of the black solid line in the steady state range, and the other term is the intercept, defined as I subscript 2, which is the intercept from the steady state region back to the intercept, or for a load cycle of 1. The slope of the relationship is first determined in the steady state range, in the steady state region. After the slope is determined, the slope is then used to estimate the intercept from the steady state range as shown in the illustration by the dashed line. Both values can be used as inputs to the MEPDG. The rut depth transfer function included in the MEPDG is shown on the slide, along with the two parameters derived from the laboratory test results. This slide illustrates the repeated load plastic deformation test results for one temperature. The upper graph shows the axial plastic strain, cumulative, measured on a confined or triaxial test specimen. The lower graph includes the process data. The process data is determined by calculating the average rate of plastic strain accumulation with the number of load cycles, using a moving average type of an approach. This analysis technique is used to determine the average slope where the rate of change is constant. In other words, the steady state range, like the flow number determination included in AASHTO T378. The data acquisition system is used to determine the two parameters from the plastic deformation relationship for a single test temperature. The slope of the relationship is first determined in the steady state or secondary region. This is done by calculating the average rate of change of plastic axial strain using a moving average technique for the average number of loading cycles. After the slope is determined, that value is then used to estimate the intercept from the steady state region as shown in the illustration by the dashed green line in the upper graph. Both values can be used as inputs to the MEPDG asphalt rut depth transfer function, which is also illustrated on the slide. This slide provides an example or illustration where repeated load plastic deformation data over multiple or 3 test temperatures were measured in accordance with the draft AASHTO standard method of test, like NCHRP report number 719, on an asphalt mixture using the asphalt mixture performance tester. A standard practice was prepared for AASHTO to provide guidelines for interpreting the outcome from the repeated load plastic deformation test to derive the plastic strain or rut depth coefficients to be entered in the PMED software. The AASHTO standard practice is available from AASHTO. The outcome from the test is defined as the slope and intercept of this relationship within the steady state or secondary range of accumulated plastic strain versus number of load cycles as shown in the chart on the left. The plastic vertical or axial strains are measured and accumulated with the number of load cycles. The result is a relationship between the number of load cycles and accumulated plastic strain for each test temperature. The 3 test temperatures were used for this test as shown in the chart on the left. None of the test temperatures exhibited the tertiary flow or tertiary region or an increasing cumulative plastic strain at an increasing rate. So none of these specimens at each of the 3 temperatures exhibited the tertiary region. The slope term, or the exponent for the number of load cycles within the steady state region, were determined for each temperature and test specimen, and the average slope term S sub t, or the coefficient B, is plotted as a function of in the upper chart on the right. The slope is temperature dependent, or the slope can be temperature dependent, but the PMED software only uses one slope term in the asphalt rut depth transfer function. In other words, the slope coefficient is assumed to be temperature dependent. The NCHRP report number 3719 provides guidance on determining the average slope when this condition occurs. So guidelines are provided to determine the slope to be used in the PMED software when the slope is found to be definitely temperature dependent. The intercept from the steady state region is determined for each temperature and test specimen, and the average intercept term I sub t, or the coefficient A, is plotted and displayed in the lower chart on the right. The intercept term is temperature dependent. The temperature exponent is determined from the intercept derived for each test temperature and region. The temperature term is illustrated by the difference or increase in the cumulative plastic strain between the different test temperatures as displayed in the chart to the right. So the slope term or exponent is determined in the steady state range. From the steady state range, the intercept term or coefficient A is derived from the intercept from the steady state, and then the temperature term and or exponent is derived based on the spread of the cumulative axial strain within the steady state range versus the number of axial load cycles. This slide provides an illustration where the repeated load plastic deformation test was measured on an asphalt mixture in accordance with NCHRP report number 719. The plastic vertical or axial strain and total strains are measured and accumulated with the number of load cycles for 3 different test temperatures. The 3 test temperatures used in this illustration are 20 degrees centigrade, 48 degrees centigrade, and then the midway temperature of 34 degrees centigrade. The result is a relationship between number of load cycles and accumulated percent plastic strain as defined by using 3 test temperatures. The outcome from the test or the inputs to the PMED asphalt rut depth transfer function and are defined as the intercept of this relationship, basically K1, from the steady state region or the secondary range of accumulated plastic strain versus number of load cycles, again defined as K1. The temperature exponent or intercept temperature dependency, the intercept temperature dependency term defined as K2, or the exponent of the temperature term, and the slope or exponent to the number of load cycles defined as K3, or the exponent to the number of load cycles. This information will be referred to in Module 6 on flexible pavement design for asphalt layer rutting. This table shown on this slide provides the global coefficients for the asphalt rut depth transfer function for all dense graded asphalt mixtures. Only one set of coefficients were derived and used in the global calibration process because the majority of the test sections used in the calibration were for dense graded neat asphalt mixtures. So the intercept of K1, a negative 2.45 in terms of mils per inch, the temperature exponent K2, 3.01, and the exponent for the load cycle, or in the steady state region, of 0.22. The lower table on this slide provides the coefficients for the asphalt rut depth transfer function derived for an individual agency that completed the repeated load plastic deformation testing and found the coefficients to be dependent on selected parameters of the asphalt mixture in their specifications. These results were used to build their XML asphalt material library files for use in design. So the intercept of K1 was found to be a function of the fine aggregate angularity, as well as the number of gyrations for the wearing surface. Only one set were defined for the base layer. The temperature exponent K2 was also found to be a function of fine aggregate angularity and number of design gyrations. And then the load cycle exponent, or K3 term, was also found to be a function of the fine aggregate angularity and the number of in-design gyrations for the wearing surface mixes, but a constant value was derived or exhibited for all asphalt base layers within that agency. This section now focuses on measuring the fatigue strength of asphalt mixtures and deriving the fatigue strength coefficients of the lower or asphalt base layers. The fatigue strength of asphalt mixtures is measured in accordance with AASHTO T321 using the bending beam fatigue test. The fatigue strength coefficients that are entered in the PMED software are derived from the measured fatigue strength over a range of temperatures and tensile strain levels. A standard practice was prepared for AASHTOware that provides guidance in deriving fatigue strength coefficients. This section discusses the input variables and values, while Section 6 on flexible pavement design discusses use of these inputs to predict bottom-up fatigue or alligator cracks. The flexible beam fatigue test standardized by AASHTO T321 has been used for years for fatigue performance analysis. This slide summarizes testing conditions of the bending beam fatigue test. The testing of one beam specimen is conducted at one temperature and one strain level. Multiple beam specimens are tested at different temperatures and different strain levels. A flexural fatigue test apparatus is also shown on the slide. The top photo shows a close-up of the test apparatus. The test apparatus is shown in the test specimen is shown in the test machine in the bottom and top apparatus. A small closed-loop servo hydraulic top one or servo pneumatic, the bottom test machine, is used with highly specialized 4-point loading fatigue fixtures that are very expensive to manufacture. These test specimens are 15 millimeter thick by 63.5 millimeter wide and 375 millimeter long rectangular beam-shaped specimens compacted using either kneading, vibratory, linear, or rolling wheel compactors. Beams cut from in-surface pavements can also be tested. However, the test is typically conducted on laboratory compacted specimens because of the variability of the mix measured in the field or exhibited in the field. The test is typically conducted at a frequency of 10 hertz and at the intermediate temperature, such as about 68 degrees Fahrenheit. The test is a 4-point bending beam test that can be either a stress or strain controlled mode. Stress controlled mode is commonly used. The test result or outcome from AASHTO T321 include flexural stiffness, dissipated energy, and the number of load cycles to a given failure criteria. There are two definitions of failure that have been used and are applicable to AASHTO T321. The one that was applied in determining the global fatigue strength coefficients for calibration is the reduction of stiffness of 50%. So the test is run past 50% of the initial flexural stiffness, and failure is defined at a stiffness reduction of 50% from the initial load cycles. The test exhibits high variability, so at least 3 temperatures and 3 to 4 tensile strain levels are recommended for use. The test temperatures typically used are 10, 20, and 30 degrees centigrade, and the tensile strains typically used vary from 200 to 700 microstrains. This slide provides an illustration of the test results from testing one asphalt mixture using Asphalt T321, or the flexural bending beam specimen. A standard practice was prepared for ASHTO to provide guidelines for interpreting the outcome from the fatigue strength test to derive the fatigue strength coefficients of the bottom-up fatigue cracking transfer function to be entered in the Pavement ME software. The ASHTO standard practice is available through ASHTOware. The outcome from testing asphalt beam specimens at one temperature and different tensile strain levels is defined as the slope and intercept of the applied tensile strain versus the number of load cycles to failure, as shown in this chart. In other words, applied tensile strain to the number of load cycles to failure. Again, failure is 50% of the initial flexural stiffness of the beam, and this would represent one test temperature. The 1 point to the right, or at 1 e to the 10 to the number of load cycles, represents the strain level for which no failure occurred, or defined as the endurance limit. The endurance limit will be discussed in a later slide. The result from this test is a relationship between the number of load cycles and tensile strain for a specific temperature. The slope, or the K2 parameter, are derived from regression analysis between tensile strain and cycles to failure. The intercept, K1, is defined as the slope or exponent of the tensile strain and is the K2 parameter as displayed on the relationship. So the slope of this relationship is the K2 parameter. The intercept of this relationship is the K1 parameter. And I may have said that incorrectly initially. So repeating it, the slope of this relationship on a log-log scale is the K2, or the exponent of the tensile strain relationship, and the intercept of this log-log relationship is the K1 coefficient. This chart provides an example of test results from Asphalt T321 for 3 temperatures of 10 degrees centigrade, 20 degrees centigrade, and 30 degrees centigrade. 4 tensile strain levels were used for each test temperature. The results from the regression for each set of temperature data are displayed on the chart. So a regression for each set of data, temperature data. The coefficients of bottom-up fatigue cracking transfer coefficients are derived by combining all of the test data into one regression equation that also includes temperature. And that is combining them into one set is shown here. and temperature is replaced by flexural stiffness because the flexural stiffness defines failure. So K1 is the intercept, K2 is the slope, the average slope of all of these relationships, and then K3 is basically the difference or the divergence in the intercept between the three test temperatures defining failure. This chart provides another example of the test results from AASHTO T321 for three test temperatures of 10 degrees, 20 degrees, and 30 degrees centigrade. 4 tensile strain levels were used for each test temperature as for the previous example. However, the test results for 10 and 20 degrees centigrade display about the same relationship or produce the same relationship. This illustrates the amount of variability of the fatigue strength test. The test is highly dependent on the sample preparation and any defects introduced into the beam specimen itself. So variability is very high for the fatigue strength test or AASHTO T321. This chart provides another example of the test results from AASHTO T321 for three test temperatures of 10 degrees centigrade, 20 degrees centigrade, and 30 degrees centigrade. 4 tensile strain levels were used for each test temperature as for the previous example. However, the test results for 30 degrees centigrade display a completely different relationship compared to the other two temperature levels, 10 and 20. This is another illustration of the amount of variability of the fatigue strength data. Deriving the fatigue strength coefficient of the transfer function can be very frustrating and time-consuming and result in significantly different values compared to the global coefficients derived from the combined testing of many different asphalt mixtures used in the global calibration process. As noted at the beginning of this section, a standard practice was prepared for AASHTO deriving the coefficients from the fatigue strength AASHTO T321 for the bottom-up fatigue cracking transfer function. This table, shown on the slide, provides the global calibration coefficients for the asphalt bottom-up fatigue cracking transfer function for all dense graded, or let's say neat dense graded asphalt mixtures. Only one set of coefficients were derived and used during the global calibration process because most of the test sections used in calibration were for dense graded neat asphalt mixes. So the intercept, 3.75 mils per inch for K1. The strain exponent of K2, 2.87. The temperature exponent, K3, of 1.46. The lower table on this slide provides the coefficients of the asphalt bottom-up fatigue cracking transfer function derived for an individual agency that completed bending beam fatigue tests and found the coefficients to be dependent on selected parameters of their asphalt mixture specifications. These results were used to build their XML asphalt material library files for use in design. So the K1 intercept in terms of mils per inch compared to the global value for this agency were found to be dependent upon the fine aggregate angularity and number of in-design gyrations. The strain exponent K2 was found to be independent of the fine aggregate angularity and the number of gyrations. Their tensile strain exponent of 2.95 is compared to 2.87 of the global calibration value. The temperature exponent of K3 was also found to be independent of fine aggregate angularity and number of design gyrations. Its value for the agency was found to be 1.61 as compared to the K3 value from the global calibration of 1.46. Just to give some comparisons between different mixes produced by different agencies. The endurance limit is another asphalt fatigue property that was discussed at the beginning of this section and is included in the PMED software. The endurance limit is schematically illustrated in the chart and is defined as the strain level at which no fatigue damage or additional fatigue damage occurs. So the flexible bending beam under repeated loads, cracking never occurs, or the beam will never fail on a practical basis. Remember at the beginning of this section, the endurance limit was not considered during the global calibration of the bottom-up fatigue cracking transfer function, so it should not be considered or used in design. If the endurance limit is used in calibration or through the calibration process, then it could be used as a design input for the mixture fatigue strength. And as shown here, the endurance limit for this one temperature and set of mixtures would be about 58 mils per inch or microstrains for this temperature and mix. So again, the endurance limit is defined as the strain level at which no damage accumulation occurs for cracking. So the bending beam will perform basically forever without cracking. A surrogate test has been used to derive the bottom-up fatigue cracking transfer function because of three major reasons that are illustrated on this slide. The first is AASHTO T321 can exhibit a lot of variability in the test results between the tensile strain levels and temperatures, as was displayed on some of the previous slides and examples. Preparing bending beam specimens is critical and needs to be absent of any defects. Preparing beam specimens also takes time and a lot of effort. The third is the time to test the bending beam specimens to failure can take a lot of time and is very labor intensive, especially for the lower strain levels. where the bending beams may require 5 to 10 million load applications prior to failure. As such, the indirect tensile strength failure strain and dynamic modulus test have been used to estimate the coefficients of the bottom-up fatigue cracking transfer function, which will be discussed and explained in the following slides. The indirect tensile failure strain and dynamic modulus test for the same testing temperature are the two parameters used in estimating the fatigue strength coefficients. The indirect tensile strength test is measured in accordance with ASTM D6931 as displayed on the upper left graph. ASTM D6931 is modified or was modified to add the LVDTs to the faces of the indirect tensile specimen and measure the horizontal and vertical displacements in accordance with AASHTO T322, but at the intermediate test temperatures. The measured horizontal displacements are used to determine the tensile strain at failure for multiple test specimens, as shown in the graph. This shows increasing strain by applying a load and increasing stress. And when failure occurs, then the failure strain is determined at that condition. So that becomes the failure tensile strain. The uniaxial dynamic modulus test, or the triaxial dynamic modulus test, is measured in accordance with AASHTO T378, which is displayed in the chart to the right. A loading frequency of 10 Hz is used because 10 Hz is used in AASHTO T321. The dynamic modulus test was discussed in an earlier section of this module. The two test outcomes of tensile strain at failure and dynamic modulus at the test temperature and a loading of 10 Hertz are combined to determine the relationship between tensile strain at failure and dynamic modulus. This shows the log of dynamic modulus versus the log of tensile strain at failure in mils per inch. This relationship is used to estimate the coefficients of the bottom-up fatigue cracking transfer function. The standard practice prepared for AASHTO provides more detail on deriving the fatigue strength coefficients from the tensile strain at failure versus dynamic modulus graph. This slide includes a short video clip of the indirect tensile stress in accordance with ASTM D6931. The video clip shows the face of the IDT specimen without the LVDTs attached to the face of the specimen. The LVDTs to measure the horizontal and vertical strains along the diametral axis must be attached to the specimen face to determine the tensile strain at failure. The LVDTs are attached to the specimen in accordance with AASHTO T322. This video illustrates the crack occurring at an intermediate test temperature to see the crack occurring along the diametral axis. At the higher test temperature, the crack will typically propagate around the larger aggregate particles. The test should be stopped when the cracks start to occur or when the indirect tensile strength starts to decrease to prevent damage to the LVDTs. Or stated differently, the test should be stopped when the load starts to decrease to prevent damage to the LVDTs. This section now focuses on the asphalt properties that are time dependent. However, what does time dependent mean? Time dependent, the asphalt properties, time dependence of the asphalt properties can refer to two characteristics, or do refer to two characteristics. The first, the properties that are dependent on the time of loading or frequency, like dynamic modulus and creep compliance. These properties and the impact of time or frequency were discussed in earlier sections of this module. The properties that change over time from year to year is the aging impact. In other words, the properties change over time due to aging and or hardening of the asphalt binder. This section briefly overviews and summarizes the properties that change over time or age. In other words, the aging and or hardening properties of the asphalt mixture. The time-dependent properties entered in the PMED software are grouped into two categories: short-term and long-term aged properties. Short-term and long-term aged properties. The short-term aged properties for measuring the asphalt properties include dynamic modulus, repeated load plastic strain coefficients, and the fatigue strength coefficients. The long-term aged properties for measuring asphalt performance were supposed to include the indirect tensile creep compliance and indirect tensile strength. However, all mixture response and strength properties representing short-term aged mixtures were grouped or were included in the global calibration process. So, short-term aged conditioning is used in preparing the asphalt mixtures for testing the response and strength properties of asphalt mixtures. This includes dynamic modulus, repeated load plastic strain coefficients, fatigue strength coefficients, and the indirect tensile creep compliance and strength. The only property that changes over time is dynamic modulus, and the change is based on solely on the binder properties, temperatures, or the mean annual air temperatures, and air voids, the in-place air voids of the mixture. So at the beginning, at the time of construction, the asphalt mixtures properties entered into the PMED software are short-term aged properties for the response and strength coefficients for the transfer function. The PMED software then only ages the dynamic modulus over the design life of the structure. And that aging is dependent on time or years, as well as depth within the flexible pavement structure or asphalt layers. The binder properties and the temperature determine the aging of the asphalt binder. This chart simply illustrates the change in dynamic modulus of the asphalt layers throughout the flexible pavement structure. You can see the effects of aging based on from pavement ME. This is a constant climate condition. The climate is constant with a high temperature. So the top 1.5 inches of the pavement ages much more and is simulated by the red kind of dashed line. And it ages more than the bottom of the pavement structure. Also, you can see that the effect of aging is much quicker in the earlier years of the pavement versus the latter years. In other words, the modulus increases, but at a much decreasing rate of increase over time. The aging model used in the PMED software is called the Witzak-Mirza aging model. It uses binder and volumetric properties of the materials in the aging predictions. The key point is that different asphalt ages differently, or different asphalts age differently, and you need to consider differences for a particular application. The other key point to make is that there is still debate on what short-term procedure is supposed to simulate short-term aging, which is production and construction with or without some service life. Long-term aging has been defined as 10 years of service life, but the long-term aging process used in the laboratory does not distinguish between wearing surfaces and underlying asphalt base layers. The long-term aging procedures were developed for the wearing surface or layer, wearing surfaces at or near the surface. So in summary, the aging function included in the pavement ME for asphalt mixtures only applies to dynamic modulus, and there's more aging at the surface than in the underlying layers, and that is the only input variable aged over time or throughout the design life of the pavement structure. So in summary, this slide lists the asphalt mixture properties that change over time or age, and those that are constant throughout the design life. Dynamic modulus is the only property that increases over the design life and is dependent on the depth of the asphalt layer in the pavement structure. The other mixture properties are constant over time and are determined based on short-term aging conditions. So this section summarizes or provides a summary of the asphalt layer inputs and how to determine those inputs. In summary, these are the test procedures used to measure the asphalt layer strength and response property inputs needed for the PMED software. The test procedures for each layer property are listed in tables 10.2 and table 10.3 in the manual of practice for the MEPDG. In summary, these are the test procedures used to determine the asphalt layer component and volumetric property inputs needed for the PMED software. The test procedures for each asphalt layer property are listed in tables 10-2 and 10-3 in the MEPDG Manual of Practice. In summary, these are the test procedures used to measure the asphalt layer. More recent binder property inputs needed by the PMED software. The test procedures for each layer property are listed in tables 10-2 and 10-3 in the MEPDG Manual of Practice. Again, please note the multiple stress creep recovery asphalt designation will not be available in the software until it's the version released in July 2024. 2024. In summary, these are the test procedures to measure the asphalt layer thermal property inputs needed for the PMED software. The test procedures for each asphalt layer property are listed in tables 10-2 and 10-3 in the MEPDG Manual of Practice. As a reminder, the asphalt layer design is completed 1 to 2 years prior to construction, so the asphalt contractor or even project materials are not known at the time of structural design. The asphalt layer properties, represent the average values expected after construction and are based on the material specifications. Again, they represent average values at the time of construction. The agency's construction database from recent projects can be used to determine the average values for design and are typically included in the XML asphalt material library files to be used in structural design. There were 5 learning outcomes for Module 4.4.5 on the properties of asphalt mixtures that are needed for structural design. The first learning outcome was simply to list the asphalt layer properties required by the PMED software for flexible pavement design. The second outcome was to discuss determination of the representative asphalt material properties. Again, the asphalt properties determined at the time of construction, and those asphalt properties represent short-term aged conditions and do not represent mixture design conditions in the laboratory. The third outcome was to explain the change in the asphalt mixture properties over the design life. The fourth outcome was to describe determination of the plastic strain or rut depth coefficients of the asphalt layer rut depth transfer function that can be measured in the laboratory. The fifth and final outcome was to describe determination of the fatigue strength coefficients of the bottom-up fatigue cracking transfer function that can also be measured in the laboratory via the AASHTO T321 bending beam flexural test and or the surrogate indirect tensile failure strain test, ASTMD 6931, and a dynamic modulus test of AASHTO T378. This ends Module 4 in its entirety. on the inputs to the PMed software. The next model of the training course or workshop sequencing will be Module 5 on rigid pavements, including jointed plain concrete pavement and continuously reinforced concrete pavements in terms of the design or distress transfer function included in the PMed software for designing rigid pavements.